Hello students, welcome back. Previously, we went through a lot of interesting properties of expected value and variance, but we didn't prove any of those. And here we go. We're going to start proving some things. This is just alternative expression of the variance and standard deviation. Standard deviation is not really important for our purpose, because all you have to do is to take the square root of the variance. So variance is the key in terms of all kind of proof problems. Now, here are the things we'll have to do. And again, this one down here is not very important. Just establish the previous expression for variance, and that's it. All you have to do is just square root and you get that. So basically we have to do 3. This, and then that. Alright, here we go. So we start from expected value of this new random variable. So therefore, oops, I clicked the wrong key. So this is basically from the definition. You have to do this. Except that this h is linear function ax plus b. Make sense? So here this is going to be ax plus b. As a matter of fact, I screwed up. This should have been here, and this should have been the conclusion. Okay, this is what we want to prove, and left-hand side will become like this. And then we have to manipulate, and see if we end up with this. Okay. Alright, how do we manipulate? Well, this is just summing up all those things. And here we have an algebraic expression. So let's just go ahead with some algebraic manipulation inside. So this can be written as pi and then b times pi, like this. And then this is summing them all up. So addition is commutative. So whether I add all these first and then all those later, or add those first and then all those, doesn't matter. So we can separate like this. Make sense? Just a little bit more manipulation. I can get this a out. It's just distributive law. That's common to all those products. So I can take this b out. Oops. Of distributive law. And then what is this? What's this? This one. That's the expected value, isn't it? Sum of all the products, payoff times probability. This quantity here is the expected value. This one. Next, what is this? Sum of all probabilities for entire sample space, that's always 1. You're adding up all the probabilities, all the probability masses, so it's going to be 1. and that'll give you this quantity. Do I have enough space for that? Okay, there you go. A little bit better proof is actually here. Oh wow, it's really simple. Okay, I guess I skipped some steps, that's why it looks simpler, but as a matter of fact, it's this one. Alright, at first step here, we used the idea of composite expected value, or expected value of composite random variables. Some function expression of payoff times the probability part, which always stays the same. Probability part always stays the same. The pi part is always the same. And this function in this particular case is ax plus b. So we put ax plus b in place of just xi. And then just manipulation here. Multiply by pi and then separate. And then take a out, take b out. Take a out. This is nothing more than expected value itself, which I just highlighted in red. And this one is actually 1. Oh, not enough space for that. That's 1. So that completes the proof. Okay, 1 down, 2 more to go. This one is not really important because all you have to do is to get this one and take the square root. So let's focus upon this one only. Alright. V of ax plus b By the way, what is variance? Variance is obtained by subtracting the mean, get the deviation, and square, and then multiply probability and adding them all up, right? So it's this. X minus mu squared. So it's expected value of this composite random variable. Make sense? This is the definition of the variance. And this expression here, x minus mu squared, that will be my new random variable if I use this expression, this idea. So what is this? This is expected value of ax plus b minus, what is the expected value of this random variable? We did it over here, didn't we? It is a mu plus b. Okay, there you go. This one is variance of this, so this, minus expected value of this, so it's over there. Yeah, we did it here. This one here, this guy here is mu. Expected value of x is mu. You see, this is mu. So mu. So a mu plus b goes here. So this minus expected value squared is this computation we have to do. Oh boy. Alright, so what do you have to do? And then we have to do this. Oh, looks like this is going to be complicated. I don't think I can do this in a single line. I'll have to use multiple lines, and there you go. So many lines, alright. So, okay. This minus the expected value of that is a mu plus b, alright. And then that thing squared. And then we have this pi, that's always stay the same, you see. This pi is always there, no matter what h of x is. that pi is also always there. And then, of course, we have to manipulate this algebraic part. And let's go ahead and do that. A part together and b part together. So a and then b minus b. Oh, great. That part cancel out. And I get only this part. A squared x minus mu squared. A squared is nothing more than a constant. I can take it outside of all the summation here. Get it out, and then what's left is, oh boy, this is nothing more than the variance. Variance of x. There. We get a squared times the variance of x. That's what we originally wanted to prove all along, wasn't it? Yeah. And then as for the standard deviation problem, all I have to do is take square root, so no problem there. Now how about this one? Variance is expected value of squared minus square of the expected value. This too is gonna be long, so I don't think I can do it in a single line, so I guess I better just open it up. Okay, this is the definition of the variance, x minus mu squared, and then times the probability. This is deviation squared, isn't it? Let's manipulate that with complete square like this. So basically this is a minus b squared, so a squared minus 2ab plus b squared. Okay? Alright. And then if I distribute this pi, so this one pi like that, and of course I can separate all those additions. Now what is this? This is expected value of x squared. You see this h of x is x squared function. So the first is all set. Next, how about this one? Well, here's 2, so take it out. Mu is also constant, so take it out. And what's left is sum of x times p, payoff times probability, and then add them all up. Oh, that's mu. This is expected value, this is mu. So this is mu times mu. So this is actually 2 mu squared actually. Now how about the third part? Well, I can take mu squared out as constant, and sum of those probabilities, that's always 1. So this is mu squared. So we have 2 mu squared and then plus mu squared, so we have just mu squared subtracted out. And this is actually mu. But then again, I wrote e of x squared, so just for aesthetics, people tend to write like this. Expected value of x squared minus square of the expected value. Expected value e of x is actually same as mu, so I could have written as expected value of x squared minus mu squared, but it's more customary to write like this, just for aesthetics. So we proved all these, and one more to go. Now all these, well, I went through these proofs, but I have never written these proof problems in exams or homeworks anywhere, and probably I won't start now because those are tedious. Each step is elementary, it's just tedious. But this one, however, I have written these kind of things in exams a number of times. The reason why this is so important will be discussed a couple of weeks later, but for now let's focus upon this. Okay. First proof is using the properties that we could establish beforehand. So expected value is, let's see, this is nothing more than, okay, I can manipulate 1 over sigma x minus mu over sigma. And then here, I can use this property here. So A expected value plus B like this. And then, okay, 1 over sigma, and then expected value. And then plus B is minus mu over sigma. But then again, this is mu. So we have mu over sigma minus mu over sigma, that's 0. So you see, this is mu. So we end up with 0. So using this, we can prove it. Variance is a little bit more complicated. No, not really. Not that complicated either. You can get it from here. Yeah, I can rewrite into ax plus b form like this. And then as you can see, plus b just disappears and we just have this one squared, so 1 of sigma squared. But then again, v of x, variance is sigma squared because sigma is standard deviation. So 1 over sigma squared times sigma squared, that's 1. So I can use this one for expected value, this one for variance. And it works, but then again, in order to do this, you have to do those first, and they were time consuming. Now what about the direct method? Expected value, well, let's see. Expected value of this, so this expression times pi, and this is h of x basically. And then let's manipulate. I can take sigma out, so let's put pi in there. And then here I can take sigma 1 over sigma out. What's left is x times p, and that's mu. Now about this part, I can take mu out, sigma out, and what's left is sum of all the probabilities, that's 1. So what do we have? Yes, mu over sigma minus mu over sigma, that's 0. Complicated? Yeah, I know, but I've written this in the exam before. To tell the truth, not this version. I wrote integral version. Alright. How about the next one? Variance. Similar. And we have this pi, but this minus expected value squared. But the expected value is 0. We just proved it. You see, we proved it. It's 0. So we don't have to consider 0 squared. It's just this whole thing squared. This part just drops out. Take sigma out, then 1 over sigma squared is there, and what's left is x minus mu squared. Wait a minute, this is just deviation squared. So this whole thing is just variance, sigma squared. So we have sigma squared over sigma squared, that's 1. So there goes the proof. And I'm not kidding, I wrote this problem before, but in all fairness, not this very version, but integral version, the integral version for continuous random variable, and that looks a little bit more benign because students have been dealing with the integrals a lot more since Calculus 1 than the infinite series that you started from Calculus 2. So integral version is far more benign. Still, deep down, this kind of things are hidden. Let's see, do we have another topic here? Mean variance and standard deviation of population. Yeah, it turns out that for a finite sample space, when the probability is given by relative frequency, then expected value is population mean, and probability standard deviation is the same as population standard deviation. Here's a proof, but it's for interested students only. Okay, I'll say section 4 is done. Thank you.